Now we will discuss second test in chi-square test. So the name of this test is chi-square test for goodness of fit. So for a given frequency distribution or data, we try to fit some probability distribution. Since there are several probability distribution, which probability distribution will fit properly may be a question of interest. In such cases, we want to test the appropriateness of the fit. And chi-square goodness of fit test is a non-parametric test that is used to find out how the observed value of a given phenomenon is significantly different from the expected value. In chi-square test of fit test, the term goodness of fit is used to compare the observed sample distribution with the expected probability distribution. Chi-square goodness of fit test determines how well theoretical distribution, so theoretical distribution means such as normal distribution, binomial distribution or Poisson distribution, fits the empirical distribution. In chi-square goodness of fit test, sample data is divided into intervals. Then the number of points that fall into the interval are compared with the expected number of points in each interval. So the measures of goodness of fit typically summarize the discrepancy between observed values and the values expected under the model in question. Such measures can be used in statistical hypothesis testing. For example, to test for normality of residuals, residuals in the sense errors. To test whether two samples are drawn from identical distributions, that is Kolmogorov-Smirnov test, or whether outcome frequencies follows a specified distribution like Pearson's chi-square test. So as you know that all these chi-square or T or any testing procedure have the few points. That means first we have to set up the hypothesis, second is to develop the test statistic, third is to find out the critical region, and fourth we need to conclude. So then what is the hypothesis in this case? The hypothesis for this test is whether fitting is good or not. So whether this fit is good or not. So that is my null hypothesis. And what is the alternative hypothesis? The alternative hypothesis in this case is fitting is not good. So in this case we compare the expected and observed frequencies. Thus we can take our H0 as there is no significant difference between observed and expected frequencies. So therefore in this case, under the null hypothesis, the observed frequencies are same as expected frequencies and that should be taken as n. So therefore the test statistic in this case becomes, so what is chi-square test in this case? So chi-square is equal to summation y minus EI square divided by EI. So what is OI in this case stands for? So OI is nothing but my observed frequencies, EI is nothing but my expected frequencies. So take the difference between OI minus EI square and square it, and it should be divided by EI. So this is my chi-square test. And again we can write this value as summation y square divided by EI minus n. So what is this n? N is nothing but total frequency, summation Fi. So take this difference of the summation y square divided by EI and n, and this value is nothing but my calculated chi-square value. So how to find out the calculated chi-square value? To find the calculated chi-square value, we are given the observed frequencies. First we need to calculate the expected frequencies, then take the difference between observed and expected frequencies, square it, and it should be divided by EI. So each value should be divided by EI, means y minus EI square should be divided by EI. And finally we have to take the total of this summation I takes values from 1 to n, y minus ai square divided by ai, and this value follows a chi-square with n minus p minus 1 degrees of freedom. So what is n? N is nothing but the total number of observations. P is the parameter estimated, and 1 degrees of freedom should be lost because of this summation y equal to summation ei. So because of this we need to subtract 1 degrees of freedom. So what is thus in testing goodness of fit, suppose if you are getting the larger value of chi-square, so that indicates the disagreement between observed and expected frequencies obtained under the null hypothesis. Suppose your calculated value is large, then we can say that there is a significant difference between observed and expected frequencies. So this means what? The critical values and the critical regions will lie towards the extreme right tail of the chi-square distribution. So therefore, the critical region in this case is probability of chi-square greater than or equal to chi-square n minus p minus 1 alpha equal to alpha. And what is this alpha? So this alpha is my level of significance. And since the chi-square test, so it is a right-tailed test, we are taking probability of chi-square is greater than or equal to chi-square n minus p minus 1 alpha equal to alpha. And how we can conclude this? So that means if calculated chi-square, if the value of calculated chi-square is greater than table chi-square, if the value of calculated chi-square is greater than table chi-square, then H0 should be rejected, otherwise accepted. Means if calculated chi-square is greater than table chi-square, so we can say that there is a significant difference between observed and expected values, and it should be rejected. And again you have to note that the goodness of fit test is always a right-tailed test. It is a right-tailed test, and the expected values for each cell needs to be at least 5 in order to use this test. So that means any cell frequency, so I mean this expected frequency should be always more than 5. If it is more than 5, then we can use this chi-square test for goodness of fit. So this is all about the chi-square test for goodness of fit, and this test is very useful whenever we are fitting any discrete distribution or continuous distribution. Thank you very much.